Okay, we're going to start 14.4, which is all about tangent planes and linear approximations. And last time we saw that we had an example that we started off with, which was this upside down paraboloid. And we took partial derivatives at the point 0, 2. Well, let's first recall what the partial derivatives were in general. These were negative 2x and negative 2y. And so at the point 0, 2, the partial derivative of x was 0, and the partial derivative of y was negative 4. And what we want to do this time is actually compute the equation of the tangent plane, because we have enough information to do that. And the way we're going to do that is to first kind of do a little generalization. So note that in general, the equation of a plane is something like a times x minus x naught plus b times y minus y naught plus c times z minus z naught is equal to 0, where maybe our point is somewhere here, x naught, y naught, z naught, and our plane may look like, something like this. And our point x, oops, let's do that in white. Our other point here is x, y, z. So this vector here, we'll call this v. V is the vector x minus x naught, y minus y naught, z minus z naught. And we're z naught here, by the way, so z0 is f of x0, y0. And this ABC is a normal vector. So ABC, we'll call this n. So n is the vector A, B, and C. So, well, let's see how we can use this to compute the equation of the tangent plane. So let's solve here in this. So let's take this circled equation. We'll call that equation 1. And let's solve for z minus z0 and then solve for z. Well, if we solve for z minus z0, well, we'll get some new constants on x minus x naught and y minus y naught. And these new constants we'll call little a and little b. Essentially here we'll divide, so from 1, divide by capital C, and then move everything to the other side. Move terms to other side. And just to make things look a little cleaner, the constants I'm just going to call, they're different. They're going to be little a and little b after we divide by capital C in equation 1 here. So this is our, and let me bring the z0 off to the other side. Z equals z0 plus little a x minus x naught plus little b y minus y naught. And let me replace here z naught with f of x0, y0. So which essentially now the only remaining task is to solve for a and b. So we need to find little a and little b. And luckily we've done a lot of the work in single variable calculus. So recall from one variable in 1D, if you're given a single point, say x naught, then the equation of the tangent line is f of x naught plus f prime of x naught, x minus x naught. This is the equation of the tangent line. So this is a tangent line. And what we can do is we can reduce our equation. Let's call this equation 2. Let's call this 2. We can reduce finding A and B to just what we know already in about tangent lines. So let's set, so from 2, let's set y equal to y0. So that now we have, well, we just have z equals f of x0, y0 plus a times x minus x0. So this is now the equation. If you think of this as just in 2 variables, if this is just 2 variables, this is a line. In fact, what does it look like? Let's draw this. It'll look something like this for us. Here is our point somewhere here is the point, let's just make an arbitrary x0, y0, and z0. If we set, so we've set y to be y0, so we've fixed a y value, we get a curve like so. And so the tangent line is just a tangent line in 1 dimension. This tangent line, what is its slope? Because essentially A is its slope. This is just the slope of the line. The slope is the derivative. So this is actually exactly the partial of f with respect to x at x naught, y naught, right? We saw that last time, that essentially when we fix y, we're looking at the change in x, and this thing is exactly the slope of that tangent line. So we get then that A is equal to del f del x at x naught, y naught. And in a similar way, if we have fixed, so in a similar way, if we fix x equals x0 in equation 2, we'll get z equals f of x0, y0 plus b times y minus y naught. And we'll get the corresponding curve, the other curve, which we can maybe do here in green. So the corresponding green curve right here, it's looks a little fat. Slim that down a little bit. So the corresponding green curve, its tangent line will be, something like this. So that the b here is the slope of the tangent line to the green curve, which is when we fixed an x value. And that slope is exactly what we found as del f del y, the change in the y direction. So what we have then is the equation of the tangent line. So the equation of the tangent plane is given as follows. Z equals f of x0, y0 plus del f del x at x naught, y naught, x minus x naught plus del f del y at x naught, y naught times y minus y naught. So in our example, so let's go back. But another way, by the way, to write this in using the other notation, which is I think what's in the book, they put f sub x here, x naught, y naught, x minus x naught plus f y. Recall that this is also a notation for the partial derivatives. And then we have y minus y naught here. Okay, so these are, if you want to sort of black box, this is the equation of the tangent plane. So going back to our example, we had z is equal to 8 minus x squared minus y squared at the point 0, 2. So that's our x naught, y naught, where the partial with respect to x was negative 2x, the partial with respect to y was negative 2y. At the point 0, 2, fx is 0, fy is minus 4, and hence our equation of the, and notice, by the way, z naught here, z0 is f of 0, 2, which is 4. So our equation of the tangent plane is z is equal to 4 plus 0 times x minus 0 plus, well, I guess minus 4 minus 4 times y minus 2. So we get z is equal to 4 minus 4y plus 8, or just 8. 4 plus 8 is 12. Oops. So 12 minus 4y. Okay, so this is the equation of the tangent plane at the point 0, 2, 4. So this is, so notice that this does cross the point x equals 0, y equals 2, and z equals 4. Okay, so let me leave you here with a little exercise. So suppose f of xy is equal to y squared e to the xy, and we're looking at the point at the point 1 ln of sorry, the other way. The ln is the x variable here. All right, so at the point x equals ln of 3 and y equals 1. And what I want is the equation of, so I want the equation of the tangent plane. Okay, we'll begin the next video with that exercise, and then we'll do the linear approximations.